And welcome everybody, lesson 9-1. So we're back in the textbook, chapter 9, first lesson of the chapter. Equivalent algebraic ratios. Let's go ahead and show you what the next couple of weeks will look like. As you can see, we are heading all the way through chapter 9. Now at some point we're going to have to jump ahead before we get to a mid-chapter quiz, but that won't be for another almost 2 weeks. So that's just giving you a little preview of where we're heading for any of you that would like to get ahead. Meanwhile, no homework to review, so let's jump right in. Our goal for the day is to give ratios of two quantities, as well as change ratios to higher terms or lower terms, whatever the case may be. Now, just a reminder, we've done stuff similar to this before when we have found equivalent fractions, whether we're looking for common denominators or whether we are simplifying fractions. So this process will be quite similar. Sooner or later, we're going to use what we know about ratios to solve any proportion problems. That includes percent problems, that includes percent of increase or decrease problems, but we first have to build the scale of finding equivalent ratios. If you'd like, pause the video, come on back when you are ready. And so heading into assignment number 13 for the day, let's go ahead and pause. I want to just review something basic because we've been working with ratios before. After all, what's the constant of proportionality? If we were to set up these ratios, $70 divided by 10, $35 divided by 5, $28 divided by 4. Whoops. Wait a second. I believe that one was supposed to be a 14. Forgive me, please. Meanwhile, that is called the constant of proportionality. What about the constant rate of change? That is when you look at how the y value compares to the x value and how they change. For instance, this goes up, the x value, the cost goes up 2, as the y value, the pounds, goes up 11. This one goes up 1. This goes up 7. This goes up 5. This goes up 35. Again, I'm going to ask your pardon for just a second. This is not working out. That was supposed to be a 14. So some of you may say, wait a second, that doesn't look the same. But if you compare the change in pounds to the change in cost, 14, the pounds go up 14 as the cost goes up 2. The pounds go up 7 as the cost goes up 1. The pounds go up 35 as the cost goes up 5. Look at that. They're once again all 7 pounds per dollar. So they are slightly different ways of examining relationships. When you do constant of proportionality, you literally just look at the ratio of the y to the x, or I suppose you could do x to y. When you look at constant rate of change, you have to first find how much it changes and then set up the ratios. But if they are constant, they should be equivalent ratios. So we're going to use those skills or build on those skills for the time being. Now, ratios are simply relationship. Boys to girls, carpet tiles to rooms, inches of snow to temperature. Now I'm going to go ahead and rotate this bag and then act like I'm spilling out some candy, right? So in this case, there is a ratio of green balls to, oh, I was going to say candy, but whatever, to yellow. And it looks to be 4 greens to 6 yellows. Although, may I also point out, you could say 4 greens to 6 yellows. You could also say 2 greens to 3 yellows, and the relationship doesn't change. It stays the same. Now I'm going to talk real quick about how to read using basically the word to. To read a ratio, read the first number, say the word 2, whether that's in place of a colon or a fraction bar or however, and then you read the second number. For instance, this relationship is read 2 to 3. To write a ratio, you have 3 choices. You may use the colon form 2 to 3. You may use the word form 2 to 3, and many of us will often use the fraction form 2 to 3. But notice, we are now talking a relationship, not just a portion. So for instance, 2 green candies to 3 yellow candies. We're not talking 2/3 of the candy. So be careful with how you understand ratios. We're not talking about parts of a pizza. We're talking a comparison of two things. All right, I'm going to skip this. This one we'll do in class. Meanwhile, let's talk about examples for how to get equal ratios. Now, this is not going to look very different for you guys. If we want to find the equivalent ratio of 9 green candies to 4 yellow candies, well, that means you'd have 5 groups of those 4 yellow candies, which means you need 5 groups of the 9 green candies. In other words, 45 to 20 would have the same ratio of yellows to greens. Now, if you wish, you can go ahead and pause and do the next few on your own and come on back. Not too concerned about numeric ratios. I believe you're going to be fine. But if I recall our class weakness, not that we're terrible at it, but it's just tougher, our class weakness is going to be algebraic ratios. Now, I want you to think about how we get from b to 3b. First thing we need is to multiply by a 3, but that only takes care of a single 3 and a b, and we need a b squared, so we might need an extra b there. Therefore, in order to get an equivalent ratio, we would have to multiply both the numerator and the denominator, both set of ratios, by 3b. So a times 3b, there's nothing that simplifies there. We will go ahead and write the variables in alphabetical order, and as always, write the coefficient first. So a to b is the same as 3 times a times b over 3b squared. All right, let's do the next one. To get from 4 to 8, we'd have to multiply by 2. To get from r to r squared, well, we're going to need an additional r, but guess what? We don't need any additional s's, so the only thing we'll have to multiply this ratio by, both the top relationship and the bottom relationship, are by 2r, excuse me. So 3 times 2 is 6, r times r is r squared, and s squared times, well, there's no additional s's, Mr. Callan, so it would be s squared left alone. Pause if you need, rewind, look at it again. Meanwhile, I'm going to do some more ratios, but now we're going to go to that old school, hey, how about lowest terms? So you would first take each of these and rewrite it as a ratio and then say, okay, what goes into both? Naturally, for 14 to 8, you could reduce by 2 and get 7 to 4. Again, so 14 girls for every 8 boys would be the same as 7 girls to 4 boys. That would be the same ratio. How about CD to C squared? Well, both of these could divide by a shared factor of C. Now, in the numerator's case, C divided by C would completely cancel out, thereby leaving a D. In the denominator's case, if you have C squared divided by C, one of those cancels out, and that would be the reason for having C in the denominator. If you wish, go ahead and pause and try these next two on your own and then come back when you're ready. So when we write a ratio of 6m squared to 8mn, clearly we can see they both share a ratio of 2. They both share a common factor of 2. They also both share at least one n. Now I wish I could say they share 2 n's, but the numerator has m times m. The denominator only has a single m. And neither of those share an n. So 2 divided by 6 is 3, and one of the m's will cancel out, leaving a numerator of 3m. 8 divided by 2 is 4, and one of the m's will cancel out, leaving a denominator of 4n squared. And we wrap up with the last ratio, in which they would both share, yes, they both share a factor of 2, but can I point out there's a greater common factor of 6. Meanwhile, they do not share an x, but they do share at least a single y. Therefore, 12 divided by 6 is 2. X divided by, well, there's no x's there, but a single y will cancel out, leaving us with 2xy. And 18 divided by 6 is 3. A single y again cancels out, leaving us with, well, actually just 3. And that's all I have, ladies and gents. If you wish, go ahead and start up assignment 13. Otherwise, I will be continuing these examples with class and happy to help. Have a good day. Let's grow.